Good morning, everyone. So let's start. Sorry, just a moment. Let's start the first part of the morning session. The first speaker is Professor Pyungwon Ko. He will tell us some thought on the dark side of the universe. So Pyungwon, please.
Okay, let me first thank the organizers for the invitation, and I'm very sorry that I could not go there today for some personal reason. I'll talk about the some thought on the dark side of the universe. And this is my overview of my talk. First, I'll talk about dark matter and dark gauge symmetry and dark Higgs boson in the Higgs portal dark matter models, and some related issues about dark Higgs bosons. Mostly today, I'll mostly talk about dark Higgs boson in dark matter physics, and this talk is based on a series of my works with these collaborators here, and I choose a few topics only from the series of my works. So I mean, all of us now agree that there is a non-baryonic dark matter in the universe. But this evidence for dark matter is all from the cosmological and astrophysical observation based on the gravitational interactions of the dark matter. And also, at the moment, we know that the cosmological concordance model or Lambda CDM model describes the present universe pretty well, but there are some issues, for example, like related with the Hubble parameter, etc. And so, in short, the dark sector landscape is composed of this, like dark matter, dark radiation, and the messengers, which carry the force between the dark matter and the standard model particles, or dark force between the dark matter and dark matter. And these messengers could be charged or neutral under the standard model gauge group. And we also need a dark energy, and we need some organizing principle for the underlying theories for this complicated dark sector landscape. And I think the following the traditional particle physics, the symmetries, either global or local, may be a good organizing principles. And here is the knowns and unknowns about dark matter. And knowns are dark matter field gravity, and this is the currently only evidence for the dark matter. And its lifetime should be much longer than the age of the universe. And mostly dark matter will be non-relativistic cold dark matter with very small pressure. And dark matter density is about 5 times of baryon density in the current universe. And local density is something like that. And it forms a halo narrow disk. But we don't know about particle physics nature of the dark matter. Like we don't know its mass or spin, and we don't know how many species there are. And we don't know any dark matter carry any internal quantum numbers or not. And also we don't know it has any internal structures, like a composite dark matter or not. And its interaction with the standard model particles, we don't know. And we don't know if it has self-interaction. So, I mean, from this list of the unknowns, we can conclude that almost nothing known about the particle physics nature of dark matter. And for the example, this is the dark side candidate in the anomalies and candidate anomalies and search techniques compiled in 2017 by US Cosmic Vision Working Group. And there are, I mean, from very light to very heavy dark matter, there are many different candidates. And today, what I'm going to talk about is mostly about in this region, WIMP. That is described by dark gauge symmetry. People often talk about portals to dark matter, Higgs portal and the UN vector portal, neutrino portal, and action portal or dark action portal, and so on. And eventually, what we observed in the experiments are portal and or missingity. Okay, so portal is one of the main component of what we observed about dark matter. And in this paper in 2013, Wanil Park and Sungwon Baek and I proposed a singular portal dark sector idea with local dark gauge symmetry, which I will describe a little bit detail later. The main point is that dark matter stability is guaranteed by unbroken local dark gauge symmetry, while longevity is guaranteed by accidental global symmetry. So in this talk, I will mainly focus on the importance of gauge symmetry and unitarity, and the role of dark Higgs bosons in association with this gauge invariance and unitarity. So we know that for the WIMPs, there are three standard search techniques: direct detection, indirect detection. Indirect detection in the current universe or early universe. This means, in a sense, dark matter relic density and the collider searches, etc. And in the experimental analysis of dark matter searches, people often use dark matter EFT or simplified model, but these are not good for collider searches. And I will show some examples where dark Higgs boson plays an important role. And also theoretical consistency such as unitarity, gauge invariance, anomaly cancellation, and normalizability can play an important role both in the standard model physics and dark model physics. So this diagram we see it very often. So chi is a dark matter and the Q is a standard model particle. So if you look at this diagram in this direction, it gives a dark matter pair annihilation into standard model particle. So it is related with the indirect detection or relic density calculation. If you look at this diagram this way, this is a direct detection, chi Q scattering to chi Q. And if you look at this direction, then this is a standard model particle pair annihilation to dark matter particles, and it's related with the dark matter search at high energy colliders. So this is a kind of crossing idea, but if you naively apply this crossing idea in dark matter EFT or a simplified model, your answer, especially in the collider searches, can be completely wrong because in each experiment, the relevant kinematic regime is very different. So this type of crossing idea can be safely applied only to the UV completed models. So especially, I will show that the dark matter searches colliders it's very important to have discuss this physics within well-defined UV completion models. And also, so I will talk about various topics, but this is one of the main result I want to show today. So dark sector parameter space, here I show dark sector parameter space for fixed dark matter mass. And in the horizontal axis, I show the M dark matter divided by M dark photon. Dark photon means some dark gauge bosons. And on the vertical axis, I show the dark matter mass divided by dark Higgs mass, okay? So if dark photon mass and dark Higgs mass goes to infinity, you will get to the origin. Okay, so this origin in this parameter space is described by a dark matter effective field theory, including the Higgs portal dark matter effective field theory. Okay, so this is in the region around here, you will have a dark matter pair annihilation into the standard model particles only by some contact interaction, and this is so this point is the EFT point. And if you include the dark photons in your model, you can start to probe the dark sector in this direction, in the horizontal direction. So if the dark matter mass, dark photon mass n gamma prime becomes smaller and smaller, then you will move from the origin to the right direction. And once you, for example, once you reach the region where this ratio is greater than 1, a new channel will open. Dark matter pair annihilation to a pair of dark photons. This will open in addition to this channel. So these two channels will be important to discuss the dark matter relic density, for example. So along this direction, you can study the dark matter phenomenology beyond the EFT approach. However, this direction, within this direction, there is no dark Higgs boson. Okay. On the other hand, if you decrease dark Higgs mass along this direction, then this direction, then the model becomes renormalizable Higgs portal dark matter model along this direction. And then in this region, dark matter pair can annihilate into a pair of dark Higgs boson. So here you can have a dark matter pair annihilation into dark Higgs boson. So and then in general, you have to include both dark Higgs boson and dark photon simultaneously. And then you can consider all any point in this plane. And for example, in this region, dark matter pair can annihilate into a dark Higgs plus dark photon. This is also possible depending on the mass relations among these three particles. So once you include dark photon and dark Higgs boson simultaneously, the new channels open for dark matter pair annihilation, and so the relic density calculation and the indirect detection signature will be changed. Okay. So here the one important thing here is this one. Once you include the dark Higgs boson, for example, for the fermion dark matter case, pi plus chi going to 5 plus phi, this becomes a P-wave annihilation. So in the later part, I will discuss that for the light dark matter case, there is a strong constraint from the CMB. And then we need a P-wave annihilation. But by including dark Higgs pair, you can easily achieve P-wave annihilation of fermionic dark matter for light dark matter case. Likewise, if you include the dark Higgs boson and dark photon, you can have a P-wave annihilation for scalar dark matter. Okay, this is a new channel which can play an important role for light scalar dark matter case. And so these two P-wave channels, this guy and this guy, these two are possible only if you include dark Higgs boson in your dark matter landscape. Okay, if you don't include dark Higgs boson in your dark sector, then you cannot have these two important channels, which can play a crucial role in the light dark matter case. So this is basically this plot is the one of the main message I want to convey to you today. So dark gauge symmetry, in many dark matter physics, people simply assume some, for example, G2 symmetry. Most common symmetry is G2 symmetry, which make dark matter stable. But there is a folklore that the global symmetry is not respected once you include gravity, classical or quantum level. This was also mentioned in the math risk talk on Tuesday morning. Basically, no global symmetry in gravity theory. So, for example, if we adopt that kind of argument, then we can consider G2 breaking dimension 5 operator of this type of operators. And if you calculate the lifetime of dark matter S from this operator, then lifetime of electroweak scale dark matter S is too short to be a dark matter candidate. So we have to forbid this type of dimension 5 operator, G2 breaking dimension 5 operator, or you have to assume this order 1 coupling is very, very small. And this argument also applies for the singular Fermi dark matter. So here is the lifetime of the singular scalar dark matter from this dimension 5 operator. So it's better to protect dark matter from decaying by some imposing local gauge symmetry rather than global symmetry. So, for example, for we can implement the G2 symmetry to U1 local gauge symmetry by replacing the singular scalar dark matter S by complex scalar dark matter X. This is a complex scalar. And we can break this U1 gauge symmetry by some dark Higgs field. But you have to choose a dark Higgs gauge charge in a judicious way. For example, if you choose the same dark charge to dark Higgs field and the dark matter like this, then you can forbid. I mean, this the previous dimension 5 operator is replaced by dimension 6 operator, and this dimension 6 operator becomes effectively dimension 5 operator after phi x develops a non-zero web. But you have an additional suppression factor from V phi over M Planck compared to the previous case. So even if you include this dimension 6 operator, you still have you can still have a very long-lived dark matter candidate, even if dark matter mass is around the electroweak scale. But in this particular choice of dark matter, you will have a problem from this dimension 4 operator. This is a gauge invariant. And after phi x develops a non-zero web, X will decay immediately to Higgs pair. So this dimension 4 operator becomes problematic for this choice of the dark charge assignment. And so the better way is to choose this charge assignment here. We assume dark matter charge is equal to 1, dark Higgs charge equal to 2, and write down all possible renormalizable and gauge invariant operators. And for this charge assignment, this term appears on U. Okay, this term is clearly gauge invariant. And when phi develops a non-zero web, dark Higgs develops non-zero web, you still have a symmetry x going to minus x. Okay, so this means that the U1 gauge symmetry is broken to G2. So this G2 is a unbroken subgroup of original U1, and this will protect dark matter from decay even if you include Planck scale suppressed operators. So by implementing this global G2 to local G2 gauge symmetry, we can have dark matters, absolutely stable dark matter, scalar dark matter. But now by making this theory as a local G2 symmetry model, the model becomes much more complicated than before. So compared to previous model, you will have a dark photon, and you will have a dark Higgs, the fluctuation of phi around the vacuum. And from this term, real part of X and the imaginary part of X will have a different masses because of this term. So you will have a two real scalar dark matter. This is assuming this guy is lighter than XR, this becomes dark matter, and this is excited scalar dark matter. So in this local jet dark matter model, you have a real scalar dark matter like in the original global jet model, but in addition, you have excited dark matter, dark photon, and dark Higgs. So three more fields compared to global G2 scalar model. And I will often today I will discuss a few examples of this type of local G2 symmetric model. And you can apply the same idea for the fermionic dark matter model too. Okay, so this model is in a sense a gauge model for inelastic dark matter model. So another idea for to introduce a local dark gauge symmetry is something like this. So we know that success of the standard model of particle physics lies in a local gauge symmetry without imposing any internal global symmetries. And electron stability is related with the Yuan electromagnetic gauge invariance, electric charge conservation, and massless photon. And the proton longevity is associated with the baryon number being an accidental symmetry of the standard model. And the proton is a composite particle made of 3 quarks. So these two are actually related with the proton longevity. Usually baryon number conservation is mentioned, but another important ingredient is the proton is made of 3 quarks. So that these two are responsible for the proton longevity in the standard model. And in the standard model, there are no gauge singlet particles in the standard model. And if we adopt this successful features of ingredient of the successful standard model to the dark sector physics, we can assume, I mean, there are some dark gauge symmetry which protect the dark matter from decay. And we don't impose any global symmetry. And once you have a gauge theory for dark sectors, your dark sector can have a very rich structure like a dark matter, excited dark matter, and dark radiation, and all force mediators. And their interactions are dictated by a local gauge principle, like standard model particles. So far, I gave some very long introduction. So here I will discuss some example of importance of dark Higgs boson. So this is a Higgs portal. I will be brief. If you have some question about details, we can discuss later. So this is a Higgs portal dark matter model in the effective theory for fermion and vector dark matter case, because it includes a dimension 5 operator for the fermion dark matter case, and it includes this mass term for the vector dark matter case, where mass term is given by hand. And this model has been studied by many groups, and for the phenomenological analysis, this model is very attractive because you can do the phenomenology with just 2 parameters like dark matter mass and Higgs photon coupling. So you need just 2 parameters to discuss relic density, direct detection, indirect detection, etc. However, I will show that we need to include the dark Higgs over singular scalar to get a normalizable unitary model, which will be important for collider search for dark matter or in certain cases. So this is a UV compression of Higgs portal singular fermion dark matter model. We introduce psi is a singular fermion dark matter model, and we introduce a singular scalar S, which is a mediator. that S couples to the dark matter as well as to the standard model Higgs field. And this is renormalizable and gauge invariant. And for the Higgs boson vector dark matter case, we give the vector dark matter mass by dark Higgs mechanism by including dark Higgs phi. And we include also Higgs boson interaction between the standard model Higgs boson and dark Higgs field. And then in these two cases, the simplest UV compressions, these two are the simplest UV compressions in terms of number of new degree of freedom. And in order to discuss dark matter physics, you need at least two more parameters, dark Higgs mass and the mixing angle between the standard model Higgs boson and dark Higgs boson. So if you expand this Lagrangian in the mass against state, for the scalar dark matter case, I mean, this is the same as the usual real scalar G2 scalar dark matter model case. But for the singular fermion or vector dark matter case, you have interaction of the both standard model Higgs boson and dark Higgs boson modulated by the sine alpha cosine alpha mixing angle here with the standard model particles and the dark matter particles. Both for the singular fermion and vector dark matter case. So you see that for the scalar dark matter, you can describe the physics with the standard model Higgs boson only. But for the fermion or vector dark matter case, you need to include the dark Higgs field. Okay. So if you simply ignore dark Higgs field H2 here, that makes the underlying theory violating gauge invariance and unitarity. So the effect of these two scalar bosons can be seen in the, for example, monojet plus missingity by reported by Atlas group, and TT bar plus missingity reported by CMS group. In the usual case, people consider only, for example, singular scalar mediator between dark sector and the standard model sector, and then the Atlas derived the bound on the new physics scale given by blue curve here. The solid line is for dark matter mass equal to 50 GeV, and the dashed line for dark matter mass equal to 400 GeV. And you know that this if you include only dark Higgs boson here, for example, you get this blue bounds. But if you include both standard model Higgs field and dark Higgs field together, then this bound change to red lines. So for the 50 GeV, you get stronger bound, and for the 400 GeV dark matter, you get much weaker bound. And this is due to some interference effect between these two form factors, between two scalar bosons. And the similar effect for TT bar plus missingity. And also collide implication from the invisible Higgs decay, upper bound on the invisible Higgs decay, you can derive the Higgs bound on the Higgs boson coupling that can be translated into the spin-independent cross-section of dark matter nucleon. And this is based on the EFT. But if you repeat this same calculation within the UV completed model, there will be two more parameters, dark Higgs mass parameter and the cosine alpha mixing angle. So depending on the dark Higgs mass, you can get the weaker bound or stronger bound for fermion dark matter and the real vector dark matter case. This dashed curve is the EFT approach. So now the last year in IJCLab, Atlas start to include this dark Higgs effect in their exclusion plot here. So for different value of dark Higgs boson, you get different bounds on this. So CMS did not include this dark Higgs effect yet, but the Atlas start to include this. But the one point is that this dark Higgs effect is important not only for the singular vector dark matter, but it's also important for singular Fermi dark matter. And one issue related with this was that the invisible Higgs decay into a pair of vector dark matter. So if you calculate this Higgs invisible decay width in the EFT, you get this result. And if you calculate the same thing in the UV completed model with dark Higgs mechanism, you get this result. And when in this expression, when you take MV going to zero limit, this simply diverges. So the result is not physical, but for the invisible decay width calculated in the UV completed model, you know, if MV is given by dark Higgs mechanism, then MV is proportional to the dark gauge coupling times V phi, and the ratio of GX scale of MV scale here is given by this form. So in the broken phase, this will be finite. Even if MV going to zero, MV can go to zero with a fixed V phi, finite V phi, if you take a GX going to zero. And the GX going to zero limit is cancelled upside up and down here. So your result will be finite. So this issue shows that the EFT can give a completely wrong result for Higgs invisible decay width into Higgs going to vector pair of vector dark matter, and this issue has been there for several years in the EFT community, and we have resolved this puzzles within the full UV completed model. So there is no problem now in this Higgs invisible decay width into a pair of vector dark matter. And the same thing also, this unitarity issue can be seen in the for example, dark matter searches at colliders. For example, dark matter pair production in ILC, we studied E plus E minus going to G star going to pair of dark standard model Higgs boson and dark Higgs boson, and this H1, H2 decay into Chi by Chi. And this work is done with Hiroshi Yokoya some time ago. And then for the singular scalar dark matter case, you have just one form factor, one scalar propagator, Higgs boson standard model Higgs boson propagator. But for the fermion dark matter or vector dark matter, you will have this type of two propagator. One is from standard model Higgs boson, second one from dark Higgs boson, and the relative sign is always minus. And then this polynomial here is a summation coming from the summation of the spin wave function of the singular fermion dark matter or vector dark matter case. And then asymptotic behavior in the full theory in the UV completed model with the two propagators is something like the 1 over t to the cube for the singular fermion dark matter, but for the vector dark matter case, it's 1 over t square by canceling these two. On the other hand, if you ignore the dark Higgs boson, and if you calculate the same thing in the effective field theory approach, you have only in both cases you have only a standard model Higgs boson propagator, so the asymptotic behavior is much larger than the UV complete case. For example, singular fermion dark matter case, it decays like 1 over t rather than 1 over t to the cube. For the vector dark matter case, it goes to constant as t goes to infinity, whereas it goes to 1 over t square in the UV complete model. So you can, from this observable quantity, we can observe that the unitarity is clearly violated in the EFT approach, but it is restored in the UV complete model. So this shows that the importance of the using the UV completed dark matter models for dark matter searches at high energy colliders. And once you have this dark Higgs boson, you can also easily accommodate galactic center gamma ray access using the Higgs boson vector dark matter model. we have for the vector dark matter pair annihilation to the standard model particle, you have this diagram, but also you can have a new channels, dark matter pair annihilating into a pair of dark Higgs boson. And if these two has a similar mass, the photon spectrum from H1 decay is similar to this case. So anyway, you can easily fit the galactic center gamma ray access using these new channels, which is possible only if you include dark Higgs boson. And last year, for the remaining few minutes, I will discuss a few things related with the inelastic dark matter, which I mentioned in detail in the beginning of my talk. So there was a couple of years ago, there was a general Nexus reported, and people usually use the one attractive solution for this was the inelastic exothermic dark matter model. So people you consider this inelastic scattering through the photon exchange, and then they introduce some mass splitting between Chi2 and Chi1 by assuming this type of hard soft breaking of gauge symmetry. However, this is not the mathematically consistent, and the correct way is to introduce a G2 symmetry, as I mentioned before. But anyway, in this case, they can consider only in order to have a light dark matter, they have to use a P-wave annihilation, which is possible only for the scalar dark matter. So, I mean, in the literature, people consider there are many studies of this XX going to G prime dark photon and going to FF bar through the P-wave annihilation and the kinetic mixing. But if we calculate the same thing within the inelastic dark matter with the U1 gauge symmetry broken G2, including the dark Higgs boson, which I explained in detail, then we have this new diagram, which is in P wave, and then you can easily achieve the P-wave annihilation as well as the correct Rayleigh density and the general Anton excess. Of course, now general Anton excess has been gone, but this idea about this P-wave annihilation for the light dark matter it still remains valid, and so it can be recycled in the future for some other dark matter physics in the future. Okay, and another important thing is that once you include this dark Higgs boson, you can also consider fermion dark matter case, inelastic fermion dark matters for general Anton excess. This is a similar model to the scalar G2 model. And then in this case, we can have the pair annihilation to a pair of dark Higgs boson for light dark Higgs field. So you can achieve correct Rayleigh density through this P-wave annihilation, as well as the explaining the general Anton excess. So there are some other examples. So here I show explicitly that the pair annihilation of these two channels are P-wave by showing this V scale factor here. So it's crucial to include dark Higgs boson to have a dark matter pair annihilation P-wave for light dark matter. Okay, if you don't include the dark Higgs boson, you cannot have these channels, and then you have to rely on, for example, forbidden dark matter, etc. But we don't have to rely on that kind of mechanism once we include the dark Higgs boson. So here is similar for LB minus L tau charge, but I don't have time for this. So here, let me summarize. Take-home message is this. Dark matter interacting with the massive dark photon is a typical scenario in dark matter physics. And the dark photon may be related with the stable long-lived dark matter, and very often dark Higgs boson has been ignored. However, there are many examples that show importance of dark Higgs boson. In this talk, I discussed the following example: interpretation of dark matter surfaces at high energy colliders, and Higgs invisible decay within to a pair of vector dark matter and the galactic center gamma ray access and general anton access, etc. And also, I didn't have enough time to touch this one, but basically the same idea. And also, I studied some years ago. I studied the Higgs boson assisted Higgs inflation, where we can have a relatively larger tensor to scalar rate ratio compared to the original Higgs inflation model. And also, I also studied a few models with the dark photon and dark Higgs, where the dark radiation interaction between dark radiation and dark matter can relax the tension in the Hubble parameter and the sigmoid in the cosmology. But in all these examples, it's very important to have include the dark Higgs boson that changes the phenomenology in particle physics and the cosmology completely. So this is the additional dark Higgs is a generic, and it improved the electroweak vacuum stability and should be actively searched for LHC and other future collider experiment. Thank you very much for your attention.
Thank you very much for a nice talk. Now it's time for question. If you have, please go ahead. Okay,
Thank you very much for your correct and comprehensive talk. I wonder what is the implication of the.
I'm sorry, I cannot hear you very well.
Can you hear me?
I can hear you better, but not very clear. Somehow the volume level in the from the auditorium is low, I think. Yeah.
See.
Yeah, please say, and
I want.
or you can write on the chatting window. Either one will be fine. Yeah.
Now, can you hear me?
Yes.
Thank you. I wonder about what if the implication of the dark matter distribution is something halo, not disk.
So dark matter, you know, the galaxy, our visible galaxy lies in the plane, forming a disc-like shape, right? But the dark matter is something like a halo. I mean, like a spherical shape around the galaxy with much bigger size. Yeah.
I meant what if the implication for the dark matter properties?
I think the somehow the dark matter how to say, in visible matter case, the matter loses its energy through the radiation effectively, and then somehow the distribution reduced becomes a disc-like shape. But for the dark matter case, that kind of energy loss mechanism is less effective and make a halo. That's what I roughly understand. Yeah.
Thank you for your answer. It is very clear.
Okay, so you Choi, please.
Yes, Professor Song Choi.
Okay, so can you hear me?
Yes, I can hear you very well.
Okay, could you go back to page 10 about these portals to dark matter?
Yes.
There. And according to this slide, you just showed only dimension 4 operators for.
Yes. Okay. Yeah. Only
and then
dimension.
can you also include some higher dimension operators for these portals?
In principle, possible, but if you have a higher dimension operator, eventually, I mean, of course, it depends on what you study, but eventually, at certain stage, you may have to consider UV completion of that. So
Of
that's
course, I
why,
agree on this that point,
so
but
that's why I listed the renormalizable portals for the first three interactions. For the action portal, you know, the effectively action has only dimension 5 operator with the standard model particles. So for the action portal, probably I will consider dimension 5 operator.
actually, the reason why I asked you this question is because now I'm working on the so-called Arapol dark matter.
Yes.
And then, so this is a kind of U1 vector portal. But instead of this dark photon field strength, we introduce some other operator, which is dimension, I think, 3 for the determinant K.
Is it related with the axial vector current?
Yeah, so this is not axial vector current. This is so-called anapole moment,
okay.
and which is completely different from vector and axial vector current.
Okay.
And then this is at least this is a 5-dimensional operator.
Yes.
If you increase the spin of this particle, then it becomes a dimension 6 or higher. And so
Yeah,
on.
I think as long as you do, I mean, if you are not interested in the collider search, high energy search,
Yeah.
then I think it's okay to consider dimension 5 operator and study the, for example, decay of standard model particle. I mean, for decay of
Yeah, simply in the beginning, we simply we want to focus on this relic density calculation.
Yeah.
And then maybe if we want to extend our work to the collider search, is probably then, according to your argument, maybe we have to be very careful, right?
Yeah, it
In
really
combining
depends.
this.
Yeah, it really. For example, your dimension 5 operator will probably come from some loop diagrams with the 3 legs, external legs. And if your collider energy is high enough to produce the loop particle at the colliders, then you cannot use the EFT approach, right? So
Yeah.
it really depends on the energy scale, etc. But at certain stage, the unitarity will be violated. So I think it's better to check the amplitude for high energy collisions in your model will be violating unitarity, and you have to check at which energy scale unitarity is violated. Okay.
Okay. Yeah.
So once you check that, then and you stay below that energy scale, it should be reasonably okay. Yeah.
Okay.
Actually, I have
thank you.
a comment on this point. These higher dimensional operators in the
Yes.
Higgs portal.
Yes.
Kimiko Yamashita, she gave a talk in this workshop about higher dimensional operators and the positivity bounds. So maybe this is related to your point in this Higgs portal case, where you could add higher dimensional operators, maybe in the effective field theory approach.
I think that I listened to her talk in Busan last October, right?
Yeah, in this workshop, she gave a talk, so you
Yeah,
can.
yeah, I know, but there's some
take a look.
I could not attend the talk. I think if I remember correctly, the main point is that I think your positivity bound is about dimension 8 operator, isn't it?
No, I mean after your comment, we included all the dimension 4,
Okay.
6 operators.
I'll study the talk slide again and talk with you later. Okay. Thank you very much.
Okay, thank you.
Yeah.
Okay. Thanks for discussion. There should be more questions, but we need to move to the next talk. So let's thank speakers.
Thank you very much.
Once again. Move to the second talk. The speaker is Clery, and he's going to talk about the gravitational portal during reheating.
Thank you. Thank you. So first, I would like to thank all the organizers for this really nice workshop. It's okay. Yeah, sure. We don't see the slide anymore, but it's okay. Glad to be here, and I want to thank you for this invitation to present my work here. And so today I will talk about gravitational portals at the end of inflation, more precisely during the stage of reheating after inflation. And
Is it working?
yeah, well, I think so. People on Zoom can hear me also?
Yeah, it's working.
Yeah, I think you can hear me well in the room. Yes. Okay. Sorry. Okay. And so this presentation will be based on this paper that have been released last year. So during this presentation, I will focus on these points. So first, I will come back to the reheating mechanism after inflation. Especially, I will focus on perturbative processes that can take place during this stage and to produce particles. And then I will introduce the specific possibility of producing particles through the gravitational interaction. And I will apply this framework to produce dark matter and radiation to some extent. And then ask the possibility if this kind of processes can entirely reheat the universe during the stage of reheating. And we will see which kind of constraints it can impose on the model. And in the last part, I will try to motivate the possibility that this kind of gravitational portals can be at the origin of the baryon asymmetry that we observe in our universe today through the well-known leptogenesis process. So first, let me come back to the reheating after inflation. So what is exactly reheating? It's this phase in the really early universe, which should connect the now very well motivated inflation era to the further radiation-dominated universe. So it's a phase of transition, which should explain the transition between a quasi-de Sitter phase to a thermal universe dominated by a hot plasma. So it raises the fundamental question: how can we populate the universe with radiation and matter also from the vacuum, or let's say from the inflaton sector at least? And so during this presentation, I will focus a specific model of inflation, a very generic and simple model of inflation driven by a single scalar field, which I will call phi, or the inflaton. And inflation itself will be realized when this scalar field is slowly rolling on top of its potential. But at some point, inflation should end, and we consider quite generically that this inflated field should fall into the minimum of its potential and start to oscillate coherently around this minimum. And so the important part of the potential for this talk is this minimum that we parameterize by this generic monomial term with this parameter k. And during this phase of oscillation of the homogeneous background, the key parameter for the dynamics is this parameter k, which is constraining the way the envelope and the frequency of the oscillations of this background are evolving with time. So in fact, this parameter is giving the average equation of state for this condensate during this phase of reheating. And to be able to reheat the universe, we also consider that this inflating background should be coupled to the other degrees of freedom in order to transfer its energy to them and succeed to reheat the universe. And so usually there are two main approaches to tackle the problem of particle production during this stage of reheating. On one hand, if the couplings are sufficiently small between the background and the other degrees of freedom, and if the number of occupation of the fields stay quite low, we can rely on the perturbative analysis to compute what are the particles produced during the stage of reheating. So we can compute decay rates or scattering amplitudes involving the inflaton background. But on the other hand, in some cases, for stronger coupling, it is well known that the system of coupled fields exhibits some instabilities in some region of the parameter space that can lead to efficient resonant effects that can lead to a rapid increasing number of occupation of the fields, which required a fully non-perturbative approach, usually done on the lattice. But in this talk, I will not consider this part of the particle production. I will consider very feeble coupling, and I will stay in the perturbative limit, involving only perturbative computation for the particle production. But still, even considering perturbative processes during reheating, This is a phase which is interesting because now the inflaton sector can provide a new gate to produce, for example, dark matter in the really early universe. So many models have been proposed to explain the generation of dark matter involving the inflaton sector during reheating. And especially these kind of models are part of a whole new class of mechanisms that are trying to go beyond, or at least to go beside, the well-explored WIMP paradigm for dark matter. So it is now involving the possibility to produce dark matter non-thermally, so not relying only on the thermal bath and not relying on the fact that dark matter was originally thermalized in the thermal bath. So it allows to explore a wide new range of couplings and dark matter masses. But now the challenge is to explain the origin of the weakness of this coupling between dark matter and the other sectors. But it also allows to connect dark matter to much higher energy scales that are relying in the early universe, such as inflation. And so in this perspective, in our recent work, we propose to look at a very minimalistic and simple model to produce particles during reheating, assuming that particles are interacting only through their gravitational interactions. So we know that the only evidence we have for interactions of dark matter are its gravitational interaction. So that was a motivation to look to this really minimalistic model where we consider that the different stress energy of the field can be coupled to the local perturbations of the background metric, so the gravitons, that can mediate between the different sectors to produce particles. And in that sense, it only supposes the effective approach of Einstein theory. And we consider this as pretty much minimal and unavoidable in this perturbative limit to produce particles during reheating. So this is the first kind of gravitational portal that I will discuss today. But in this perspective of exploring gravitational effects, it also appears natural for us to generalize this framework by introducing additional gravitational couplings of the fields with gravity, so which takes the form of these non-minimal couplings to gravity of scalar fields. So in our model, we consider different sectors to be non-minimally coupled to gravity. We consider the inflaton sector, but also, and more importantly, the standard model Higgs bosons to be non-minimally coupled to gravity. And it is known that performing the transformation towards the Einstein frame, this kind of non-minimal couplings to gravity provide in the small field limits additional interactions between these scalar fields that allow to produce, again, radiation and dark matter from the background field, which is the inflaton. So this is the second kind of gravitational portal that I'm discussing today, which I will refer to as non-minimal. And just to explain rapidly the simple approach we had to compute particle production during this stage, we rely on the simple transition amplitudes computation, assuming local interactions in flat background, and considering in the initial state the inflaton condensate, which is an homogeneous background, coherently oscillating during reheating. And from this transition amplitude, we can compute the rate of particle production and track the evolution of the number densities for dark matter, but also the energy densities of radiation and of the background during the stage of reheating. And in this framework, we consider different possibilities to produce particles during reheating. On one hand, particles that are already produced and thermalized into the plasma can scatter and to produce dark matter mediated by these gravitational interactions. So it's a specific case of a very feeble coupling for a THIMP scenario. But more efficiently, during reheating, the inflaton oscillation modes can, in a sense, scatter to produce dark matter mediated by these gravitational interactions that I introduced before. And the last possibility is, of course, to produce radiation during reheating from the background involving these gravitational interactions. About this last point, I want to underline now that this kind of processes involving scattering of oscillating modes cannot entirely reheat the universe, at least not in a quadratic potential. So when this inflaton field is oscillating around a minimum which looks like phi square, it's coming from a simple fact that energy density that you produce in terms of radiation in this process is decreasing faster or redshifting faster than the inflaton energy density. So you cannot reach the equality between the two. But still, this kind of processes can have an impact on the early production of radiation. So here on this plot, you have the evolution of the different energy densities as function of the scale factor after inflation. In blue, you have the evolution of the background, inflate and condensate. And in red, the production of the radiation during reheating. And the different dashed color lines correspond to the different contribution to radiation production depicted by these processes on the right. So the purple line corresponds to the minimal framework, the minimal interaction we consider, which is the graviton exchange process that we consider to be unavoidable. So it puts a lower limit on radiation production. And of course, adding non-minimal couplings to gravity, especially of the Higgs bosons, provide additional contribution to radiation production that can enhance the production of radiation in this by these gravitational portals. And so these kind of processes can dominate the early evolution of radiation up to a maximum energy density produced. But here we are considering a quadratic potential. This parameter K that I introduced before is equal to. And so the late time evolution of radiation should still be given by some inflaton decay in order to succeed to reheat the universe. So here I added this kind of decay of the inflaton in order to succeed to have a reheating in this scenario. About dark matter production by these gravitational portals, here on this plot you have the production of a scalar dark matter, a generic scalar dark matter by these gravitational portals in this parameter space given by the mass of the dark matter candidate and the reheating temperature achieved during this stage. And the different lines corresponds to the right Röhlich abundance of dark matter as inferred by Planck data. And in red, you have the contribution only from the graviton exchange process. So the minimal scenario can succeed to produce enough dark matter for really high dark matter mass and really high reheating temperature. But including non-minimal couplings to gravity, it can allow to lower this constraint and have a dark matter mass which is much smaller for non-minimal couplings which are higher. Okay, so these are the former results we had on particles production from these gravitational portals during reheating. And for the second part of this presentation, I want to come back to the reheating mechanism itself and ask the simple question, is it possible to entirely reheat the universe through these perturbative processes involving only these gravitational interactions in this minimalistic scenario? And I said earlier that it wasn't possible, at least not in a quadratic potential. But in fact, if we consider much steeper potential of inflaton near the minimum, then the inflaton energy density will decrease much faster than the radiation you produced. And so it becomes possible to reach equality between the two. And so for sufficiently steep inflaton potential near the minimum, you can reach reheating temperature which are higher than the BBN bound, and so making a successful reheating. And so now including again non-minimal couplings to gravity between the background and the Higgs boson and gravity, it allows to produce much more radiation and to reach much higher reheating temperature through this kind of gravitational portals. And so on this plot, you have the reheating temperature achieved by these gravitational effects, depending on the shape of the inflaton potential near the minimum. And the different lines corresponds to different non-minimal couplings of the Higgs bosons to gravity. And so I want to underline that this line where psi h equals 0 is the minimal framework of graviton exchange process. And so we consider this as really unavoidable and minimal. So it is giving the lower bound on the reheating temperature that you can achieve during this stage. But additionally to this bound, you see that this line seems to rely in this blue purple region, which seems to be excluded. So what is this constraint that I added on this plot? In fact, we also know that during inflation, there should be some quantum fluctuations, especially of tensor modes that will exit the horizon during inflation and will re-enter the horizon later. And for some of these modes, for some of the wavelengths associated, this mode will re-enter the horizon during reheating phase. And if during this reheating phase, the inflaton background is decreasing faster than the usual radiation plasma, then the range of wavelengths that are re-entering during reheating can have their strength enhanced. So the spectrum of primordial gravitational waves is enhanced for a range of frequency, and the shape of this enhancement, or the shape of the slope of this spectrum, depends exactly on the shape of the inflaton potential near the minimum. So it depends on this parameter K that I introduced before. And in addition to that, the maximum enhancement, so the frequency which is the most enhanced, corresponds to the mode which is re-entering right after inflation, so at the beginning of the reheating phase. So probing this distinctive feature of the primordial gravitational wave spectrum could allow to constrain the reheating process, especially the potential of inflaton near the minimum, but also what is happening at the really early phase of the reheating. And in fact, we also know that gravitational waves, when they will propagate through the universe, they will also act as additional radiation, especially at BBN and CMB time. And the current bound we have already for additional radiation at this time puts some strong constraint on the gravitational wave strength that we can have at this time. And so, in fact, the enhancement of the spectrum already excluded the minimal gravitational portal for reheating. So the line where psi h equals 0 is already excluded by too much enhancement of these primordial gravitational waves because of a too low reheating temperature. But if we add non-minimal couplings to gravity, we are producing more radiation, and it is possible to evade this bound by a non-minimal coupling of the order of 0.5 for the Higgs boson. But beyond this constraint, this kind of distinctive feature of the primordial gravitational wave spectrum can provide an important probe of the reheating phase, especially in this parameter space. Future gravitational wave experiments can probe a part of this reheating plane given the reheating temperature and the shape of the inflaton potential near the minimum. Okay. And for the last part of my presentation, I want to propose the possibility that this kind of gravitational effects in a really minimalistic approach can also be at the origin of the observed baryon asymmetry in our universe through the leptogenesis process. So we consider in our recent work that there exists some right-handed neutrinos that are also well motivated to explain active neutrino mass and to be good dark matter candidates. And these right-handed neutrinos could be produced during reheating from this kind of gravitational portals that I introduced before. And it is also well known that these right-handed neutrinos, which can be really massive, in their decay, they can provide an asymmetry between leptons and anti-leptons characterized by this asymmetry parameter, and which can be further converted into a baryon asymmetry, and so explain the asymmetry between matter and antimatter that we observe in our universe. And so for the really last part, I want to gather these results about gravitational portals and see if it's possible to have a really minimalistic framework that can simultaneously explain the generation of dark matter, the generation of the baryon asymmetry that we observe in our universe, and explain the reheating process in this perturbative unit. And in order to do that, we consider 3 generations of right-handed neutrinos. I labeled them N1, N2, and 3. We add non-minimal couplings to gravity of the Higgs boson, especially, and we consider the inflating sector again. And one of the right-handed neutrinos will be the lightest one, and we consider it to be decoupled or almost completely decoupled to be a good dark matter candidate. And the 2 other generations will be much heavier and will participate to the leptogenesis process. And the framework is divided in 3 main mechanisms. So you produce dark matter in the form of this neutrino N1 by these gravitational portals. You can include the graviton exchange process, but also non-minimal couplings to gravity. You produce the heavier right-handed neutrino, which stay out of equilibrium, and you produce them also from these gravitational portals. And finally, you produce radiation from these gravitational portals, including non-minimal couplings to gravity, to reach sufficiently high reheating temperature. So these are the results about this minimalistic scenario. Here we have the production of dark matter in the form of the neutrino N1. So the different dashed color line correspond again to the right Rayleigh abundance of dark matter. Here for each color, it corresponds to different dark matter mass. And you see that you have two set of lines now that seems to satisfy or to saturate the Rayleigh abundance. In fact, it's coming from the fact that we consider now a fermionic dark matter. So the process of inflaton scattering is helicity suppressed. And so depending on the mass of the dark matter candidate and on the bath, the rating temperature of the bath, the process of standard model particle thermalized that scatter can dominate over the production from the inflaton background. And so you have two sets of lines that can satisfy the right Rayleigh abundance, and the region between the two is the region of underabundance. The results for the production of the baryon asymmetry is quite similar. So in this plot, you have the dashed lines in colors that correspond to the right baryon asymmetry that we observe in our universe, coming from this leptogenesis process and the production of these right-handed neutrinos through these gravitational portals. And this corresponds to the colors corresponds to the different mass needed for this right-handed neutrino N2. And in fact, the question I asked before, is it possible to have simultaneously the generation of dark matter, the baryon asymmetry, and the reheating process in this minimalistic scenario, is answered in this plot. So in this parameter space given by the mass of the two lighter right-handed neutrino, N1 and N2, you have points that corresponds to the right Rayleigh abundance of dark matter and simultaneously of the right baryon asymmetry. And you see that we need non-minimal couplings to gravity in order to have sufficiently high reheating temperature. I showed before that the minimal graviton exchange process is already excluded by too much enhancement of gravitational waves. But there are still solutions to this problem with non-minimal couplings of the order of 1 or 10, and giving dark matter mass of the order of the PeV for the mass of the dark matter, and the mass of the other right-handed neutrino of the order of 10 to the 11 or 10 to the 12 GeV. Okay, so I will come to my conclusion. So in this short presentation, I tried to motivate a very simple and minimalistic scenario during reheating, where we consider perturbative processes involving only the gravitational interactions to put unavoidable lower limits on radiation, but also dark matter production during this really early universe stage. And we saw that these kind of processes can even complete entirely the reheating in sufficiently steep inflaton potential near the minimum. And we also show that the enhancement of primordial gravitational waves put already some constraint on these models and can in the future probe a part of this reheating parameter space. And finally, we saw that it is possible to accommodate the production of dark matter relic as well as the baryon asymmetry that we observe today, together with the reheating mechanism in this really simple scenario involving only gravitational interactions. So thank you for your attention.
Thank you very much for your interesting talk. Now the time for question. If you have, please go ahead.
Thank you for your nice talk. I have a question about the perturbative decay and the reheating temperature. Do you have you consider the gravitational portals for reheating? But as I remember, if you have a gravitational interaction only and consider the inflaton decay, the minimal reheating temperature that people normally quote is about 10 to the 9 GeV. Mm-hmm. So in your approach, what is the difference? Because you could get a very small reheating temperature. What is how do you estimate the reheating temperature in your case?
I'm not sure to understand. So in this case, we only consider the gravitational effects. So the scattering of oscillating modes that can produce, here the main process will be producing Higgs bosons to reheat the universe. And so in that case, we don't have inflaton decay process. We just have inflaton oscillating mode scattered to produce Higgs boson. And so if you compute this contribution from the graviton exchange process only, so involving only the graviton, massless graviton propagator, you have this reheating temperature produced depending on the shape of the inflaton potential at the minimum. So this bound is really the one at the border of the gray region is really the minimal temperature that we esteem to achieve by this minimal scenario.
So I think, yeah, but there was some discussion about the importance of the decay term, but in your case, the scattering term only. So in order to complete reheating, you need the decay term, and then probably you are assuming the decay term becomes important when the radiation and inflaton energy density become equal.
I think, in fact, the problem is that usually you need a decay term because you still have the inflaton condensate still be there even if you have scattering processes in quadratic or quartic potential. But here we are considering really steep inflaton potentials. So in fact, I'm not sure I have. No, I don't. The inflaton condensate energy density will be decreasing really fast. And so at some point you will reach the equality between the two, so the reheating process, and the inflaton energy density will be really negligible after that. So you don't need an additional inflaton decay in order to deplete the inflaton condensate. So it will be decreasing much faster, and so at some point it will not be there anymore, and not be completely negligible in terms of energy density.
In your case, the steep potential.
Yes, exactly. But so this is the problem. That, I mean, we need then a really steep inflaton potential.
Any other question? I have one question. So you introduced a non-minimal coupling for this inflaton, Higgs, and dark matter, something like that. And it's improved, how to say, the heating process, right? That is what you mentioned. So totally, which non-minimal coupling is important? Because you said they are equal. So
yeah, in fact, it was to simplify the thing, but in fact, if you want to stay in these small field limits, and if we want to consider perturbative computation, the non-minimal coupling of the inflaton is really constrained because the inflaton field is of the order of the Planck mass at the end of inflation. So if we want to make this small field perturbation expansion, it imposes that this small non-minimal coupling of the inflaton is really small. So if we want to have an efficient reheating, we need to play on the non-minimal couplings of the Higgs bosons only. And so this is this one which can be important. So in this case, this one is not important. Okay.
So the Higgs non-minimal coupling should be large somehow compared to the.
Somewhat large, yes. We considered between like 1 to 1,000. Above, it's also complicated to have really large non-minimal couplings of the Higgs bosons because you will trigger some resonance effects really efficiently. And so if you wanted to avoid this, we need to stay in a range of non-minimal couplings, but these are the range that I showed in the parameter space.
Yeah, I also wonder these other scalar fields can affect the inflaton dynamics also.
Yes, so if you include other scalar fields with other non-minimal couplings, yes, it can affect, I think, this picture. We included also the non-minimal couplings of the dark matter scalar candidate in order to produce it efficiently. And if we stay in some limits, it's not perturbing the potential of the inflaton, and it's not changing the results for the heating temperature.
Okay, thanks.
Thank you.
Any other questions? So if not, you have. If not, let's thank speakers once again.